All right, so this is a remote system for radiological survey of vertical surfaces. Senior Design 1, Fall of 2020. Team members include Brad Baer, Blake Stonestreet, Connor Rice, Patrick Clay, Alozar Shimbira, Jonathan Erdman, and Jesse Kaysen. The sponsor and mentor is Richard Reed and Tifu Zhao. This is sponsored by EPRI, Electric Power Research Institute, and UNC Charlotte. Our poster includes abstract, background, project specifications, system design, subsystem design, electrical, computer, and our future plan.
The goal of the project was to develop a system to carry a 5 kilogram radiation sensor at prescribed intervals and record findings. This entailed a system to precisely carry the sensor along horizontal and vertical axis, a system to maintain stability, a system to manage wires to prevent tangling, and a system to log locational and radiation data. This project arose when EPRI sought to automate the time-consuming task of scanning decommissioned nuclear sites. They needed a device that could attach to a mobile ground robot and adhere to its specifications.
These are the project specifications for our senior design project, and the main important factors is that it must raise a sensor of at least 3 meters high. The total system must not exceed 75 kilograms. The total runtime of our system must be at least 4 hours, and it must be completely autonomously controlled.
So the system is separated into 4 subsystems. The first is a sensor mount. This houses the radiological device used for measuring radiation. The second is the telescopic pole system. This uses 3 linear actuators to extend the device up to 3.5 meters in height. The third is a cable spool management. It is responsible for reel in and reel out cable management to keep a constant tension on the cables. And the fourth is a leg stabilizer system. This is to prevent the system from shaking when it's extended to its full height.
This slide illustrates the different subsystems of our total design. It includes a mounting base, a wire spool assembly, leg stabilizers, electronic housing, our telescoping assembly, and a sensor scanning track.
The controller first initializes all the actuators, then it extends the side stabilizers and takes a reverse measurement. Then it checks if it's at the max height. If it's not at the max height, it increases the height and takes another measurement. If it is at the max height, it resets the actuators, then retracts the stabilizers, then moves to the next location and takes the next measurement and repeats.
So the whole system will be controlled using the Arduino Mega microcontroller. The Arduino Mega contains 54 digital input and output pins and 8 kilobytes of memory. The board also has a built-in Wi-Fi which can help us in transferring the measured data.
To supply power to the robot, we chose to use the lithium iron phosphate batteries because of their greater power output and lower weight. Using the two 12-volt 23 amp hour batteries connected in parallel provides the amp hours needed to meet the 4-hour minimum runtime. This also allows the device to be recharged overnight with the option for fast charging if needed. The actuators utilize 3 4-channel 5-volt relays to power and control the actuator movement based on the control signal from the Arduino microcontroller.
Our plans for the future is to purchase all of our equipment in December, so come spring of 2021 we are able to begin manufacturing of our design, and we plan to have our robot built in March so we can have room for testing in May so that EPRI will receive a full prototype.